Hello and welcome to the Daily Space for today, Tuesday, May 5th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today we are going to be joined by CalTech scientist Andreas Faisst, who is the U.S. lead principal investigator for ALPINE, a 70-hour program that used the Atacama Large Millimeter Array to study the early universe. We recently discussed his team's latest paper on the formation of spiral galaxies in the early universe, and today he will be joining us to provide a deeper dive into the cool new science. But before we do that, let's take a look at the news. In our top news story of the day, we learned that black holes may be closer than we thought. Quite by accident, a team of double star observers has found a black hole just 1,000 light years from Earth. While studying two stars that can readily be seen in dark skies with the unaided eye, the team found motions that required a third object, an invisible object, an object that doesn't appear at all and matches exactly what we'd expect from a black hole. One of the two stars in this system appears to orbit an unseen companion every 40 days, while the outer star... I'm sorry, we are having technical difficulties. Excuse me for one moment while I pause to make that video work. Hold on, we will be right with you with the video. These are the technical difficulties that drive all of us crazy. So sorry, everyone. All right, so I'm going to go back to the beginning of that paragraph so that we all know what I was saying. So one of the two stars in this system appears to orbit its unseen companion every 40 days, while the other star orbits both these objects. This study was led by Thomas Ravenous, and he used the ESO 2.2 telescope at La Sille in Chile. This apparent black hole is well behaved. It isn't cannibalizing its companions. It isn't flaring in X-rays. It isn't doing anything other than hanging out and using its 8 solar masses worth of gravity to move around its companions. In a way, this was a lucky find. This team's careful photometry was spread out over time and was initially designed to measure the much slower motions of the outer star. While this system did let them catch all the needed position measurements to sort all 3 orbits, other systems may not have been so polite. This means that noise in several other double star systems they've observed are now being considered as potentially being consistent with there being 3 objects that include a hidden black hole. Now, back when I was in college, a guest speaker said that when we look at the stars, 4 out of every 3 stars is a binary. Now, for those of you not catching this math joke, he was referring to how so many things we look at initially appear to be individual stars, but turn out to be binary stars. Well, if you think you're looking at 3 stars in your binocular view, if you grab a telescope, you may discover those 3 stars are 5, with 2 sets of 2 lurking in the field. Today, there's a lot of debate on exactly how many stars are binaries, but it looks like those arguments are going to get a lot more complex, as we have to also ask which systems are hiding dark objects. Project lead author Thomas Ravenous puts it this way: there must be hundreds of millions of black holes out there, but we know only very few. Knowing what to look for should put us in a better position to find them. Bada adds that finding a black hole in a triple system so close by indicates that we are seeing just the tip of an exciting iceberg. Now, from a distant triple system, we turn to look at the 4th rock from the sun. In a new paper in the journal Science Advances, a team led by Anna Mitzholtz has used data from the MAVEN spacecraft to determine when Mars had a magnetic field. The verdict is 4.5 to 3.7 billion years ago. During that time, a compass would have helped you get around the red planet, and that magnetic field would have just helped you keep a little bit safer from the cosmic rays of space. To get a magnetic field, a world needs to have a liquid mantle capable of moving charged particles in a dynamo that creates that magnetic field. Or put differently, things happen that we don't really understand and have named a dynamo, and a magnetic field is generated. Really, we don't totally understand the generation of magnetic fields in planets, but we know that a molten mantle is required. When that magnetic field is in place, any rocks that form with the correct magnetically sensitive materials will align their minerals along that magnetic field, essentially recording the presence of the field and its orientation. Using MAVEN data, the team was able to measure magnetic fields coming from the Locus Planum lava flow on Mars that is believed to have formed just 3.7 billion years ago. This is the youngest fossilized magnetic field to be found, and regions created just 3.9 billion years ago show no evidence that a Martian dynamo was active at that time. This means that we are catching the field in the process of turning off in this data. This work was published today, and I haven't had a chance to fully read the paper yet. But one of the cool things not mentioned in the press release is this magnetic field would have coincided with the same period of time when Mars had water and an atmosphere, and it would have helped make Mars all that more habitable a place. Now, more than ever, I'm eager to go fossil hunting on Mars. Not that we quite have the technology, but I'm ready. Now, in our final story, we take a scientific look at an object dead in between stars and planets. This is the land of brown dwarfs. These failed stars formed like stars, but just don't have enough mass to maintain nuclear reactions that burn regular hydrogen for prolonged periods, and instead only have fitful burning of tritium or deuterium early in their lives. With masses just 13 to 80 times that of Jupiter, these objects are physically the size of a gas giant. And new observations from a team at CalTech finds that these objects may also have banding patterns not too different from what we see in gas giants. While studying Lumen 16A, a brown dwarf in a close binary just 6.5 light years away, a team of scientists saw fluctuations in brightness consistent with the presence of clouds. The initial observations were done with the Spitzer Space Telescope and looked at this object in the infrared. New observations with the European Southern Observatory's very large telescope in Chile looked at the starlight's polarization and found that the alignment of the light is consistent with the clouds being in smooth bands instead of in patchy large clouds. Now, this data doesn't allow them to know how many bands there may be. That is left to the artist, but this data does tell us that these failed stars have weather like planets. According to co-author of this study, Julian Girard of the Space Telescope Science Institute, these storms can rain things like silicates or ammonia. It's pretty awful weather, actually. Now, this work appears in the Astrophysical Journal and is led by Maxwell Miller Blancher, who points out this is the first time polarimetry has really been exploited to understand cloud properties outside of the solar system. Here is to hoping more of this kind of big science can be done with the ever-growing number of big telescopes being built around the world. When this happens, we'll bring that science to you right here on the Daily Space. And that rounds out our news for today, but this doesn't end our episode. In just a moment, I will be joined by Dr. Andreas Faisst, and we're going to talk galaxies, dust, and gas as seen by the Atacama Large Millimeter Array in a study of the early universe. So I'm going to put up that good old-fashioned please stand by video, and I would ask you to please stand by. We will be right back in just a moment. Hello, everyone, and welcome back. I am now joined by Dr. Andreas Faisst, and it's such a pleasure to have you on. After seeing so many surveys of solar system after solar system, me and my galaxy-loving heart was delighted to see the research that you've been working on. Can you give us a quick rundown of who you are and what it is you've been up to?
Of course. Hello. Thanks for inviting me. So, as you said, I'm Andreas Faisst. I'm a scientist at CalTech. That's the Infrared Processing and Analysis Center at the California Institute of Technology. I'm originally from Switzerland, so I moved to California in 2015, and I'm joining the sunny weather here. I came here as postdoc, and now I'm permanent at CalTech.
That's awesome. Mm-hmm. And it's such a great group out there. I've had so much love for so many of the different products coming out. And what's cool is IPAC looks at objects of all things near and far. That brown dwarf story we just covered came from your teams as well. Now, you went in a different direction. Infrared can tell us about warm planets, but it can also tell us about bright objects so far away in the universe that their light has been shifted from where we're used to seeing it in the visual and the infrared. The visual and the ultraviolet, all the way out into, well, millimeter and longer wavelengths. So what exactly is it that your team and ALPINE has been doing?
So ALPINE is basically, so what we are trying to do is to really look at the gas content of galaxies and how dusty they are. And so, as you said, in infrared, so the galaxies, they are far away, so their light is redshifted, which means we have to look into the red to actually see them, right? And what we are trying to do is to target 118 galaxies that are about 12 to 13 billion light years away. So they were formed about 1 billion years after the Big Bang. So they are quite young in the time of the universe. And we took this Atacama large array to look at them in the radio. And what we really can do now is we can look at the gas of these galaxies, because the gas emits at a very specific wavelength. And with ALMA, we can look at that wavelength. And in addition to that, we can also look through the dust of those galaxies. So we see what's going on behind a screen of dust of those galaxies. So basically, we can see how many stars are there forming hidden by dust, which is very interesting.
And this is cool research because it's starting to hint on things that even 10 years ago, we thought we were going to have to wait for the JWST to launch before we could study. We have been working to build that telescope specifically to answer questions about when and how do galaxies form. Well, with Atacama, we're learning that millimeter and radio wavelengths can get you there almost as well. Now, the big questions that have been plaguing us are, when did galaxies turn on, and what was the process or multiple processes by which they formed? What all kinds of often dead bug-looking forms have you found forming in the early universe?
That's very interesting, actually. So we found basically everything. So we found galaxies that are colliding with each other. For example, you see in my background, when you look in the upper tier, so those two galaxies, they are really colliding with each other. But then we also see like very kind of boring compact galaxies that are just rotating, like spiral galaxies do in our local universe, like the Andromeda Galaxy or our Milky Way. So there's a huge diversity already, 600-700 to a billion years, 600-700 million years to a billion years after the Big Bang. And this is very interesting.
And so the general story that we're looking at is there is moment zero when something triggered all of the energy of the universe and mass energy of the universe coming into being. And over about 400,000 years, a whole bunch of stuff we're going to not talk about today occurred that led to this moment in time when the matter and the light separated and our universe became opaque. But at that moment, it was pretty much just this like diffuse cloud of gas, hydrogen, helium, trace amounts of lithium and beryllium. It's a little bit lumpy, but not very much. But those tiny differences in a little more mass here, a little less mass there, led to gravity taking over. Now, where you're looking is this period of time where observationally we're finding the most massive galaxies have already like settled in, are like, hi, we're here, we're red. But regular galaxies are just in the process of coming into being chaotically through this merger of smaller things into larger and larger. And how fast this process happens has been one heck of a mystery for, well, a century. And what was the breakdown of, like, did you find mostly galaxies were still in the process of forming? Did you find what was that population that you discovered in your data?
So we still see a lot of like irregular galaxies, obviously, at this time. But we see maybe about 10 to 15% of the galaxies that are already, they have an ordered rotation, right? Which means they haven't had like a collision event in the near past. So they already basically settled down for at least that time we are looking at them, right? We don't know what's happened to them in the future, right? They might merge again with another galaxy. But they're pretty much settled down, and they're also, what we also observe with other observatories like the Keck telescopes, that some of those galaxies are very metal rich, right? And the metallicity increases over time, right? It has to build up, and the fact that some of those guys are already metal enriched means that they're already pretty much in a evolved stage at that time, which is very interesting.
And astronomers are weird. We call anything on the periodic table that isn't hydrogen or helium a metal. Yeah. So yes, to me, carbon is a perfectly reasonable metal. And all of these heavier elements have to come from generations of star formation. Exactly. So you're looking at systems that have already had multiple generations of star formation.
Yeah, that's the interesting thing, right? They basically, they have been living there for like 700, 800 million years, and they already had a good bunch of star formation and are already very evolved, right? So this is something we didn't know before, right? And with this ALPINE, we actually have now the statistical sample, right? Because people found like, one galaxy, that's metal enriched. Oh, cool. What does it tell you? Now our ALPINE program, we have 118 of those galaxies that we can actually statistically say, how many percent of them are like this or like that, right? And so this is very interesting.
Now, how many galaxies did you find percentage-wise that metallicity-wise at least would have fit in with our modern universe?
I would say it's maybe 10, 20% of them.
So 10 to 20% of the galaxies in the first 1.5 billion years of the universe were already metal rich enough to have stellar populations like we're used to with us, with Andromeda, with the nearby galaxies.
Close to, what we see today. Yes.
That is kind of amazing, and I'm really hoping that the astrobiology folks are paying attention to this, because suddenly all of the sci-fi ideas of the elder ones are completely reasonable, but that's a different story. Now, while the galaxies had star content, stellar composition similar to what we're used to, did the galaxies look like we're used to?
Yeah, so maybe you can pull up one of the slides here now for example, a slide, maybe go to slide 15.
Yep, just a second. I'm going to switch images around and I will have it.
Or maybe can you do 14?
I can do 14 and then switch to 15.
That's perfect. So basically, you can measure with ALMA this singly ionized carbon line, which is basically light emitted by carbon atoms that are heated by young stars, right? So it directly relates to the star formation of those galaxies, because if you have more stars, you have more carbon emission. So that's the connection.
And carbon is a cool element because it can be found in lower mass stars and gets emitted during all sorts of different processes. So you don't have to wait for generations of supernovae.
Exactly. It's very easily excitable. So it's basically everywhere in the galaxy, right? Which also causes a problem, right? It's not always where stars are forming, right? It can also be outside somewhere in the galaxy. But that's something we have to find out. But the cool thing is, it's mostly where it's basically tracing the gas in the galaxy. And so if we now look at this graphic, you basically see when the galaxy is rotating with the Doppler shift of the light. If we observe this carbon line, which we call C+, we can actually trace the rotation of the galaxy, right? And so on the left, you see the diagram, and on the right, you actually see a measurement that we did of that galaxy, and you see it looks a bit flat, right? So you can think of it as an edge-on disk galaxy, and you see the blue light that's coming towards us and the red part that's going away. So you can actually measure the rotation of those galaxies.
That is kind of awesome.
Yeah, and that's really cool.
I'm going to take a look at that next slide you have tantalized us with. And this really shows how it takes multiple telescopes to get at an answer.
Exactly, yeah. So this is the beauty of ALPINE, right? So ALPINE is not only ALMA, it's also, we also have data from ground-based spectrographs and other telescopes like the Keck observatories in Hawaii, or the very large telescopes, the VLT in Chile. And we have Spitzer too, right? Spitzer is also a very important thing here. So, and then Hubble, obviously, right? So what Hubble and ground-based observatories see is just the light that's emitted from stars that are not obscured by dust. So that's basically what you would see with your eyes, right? Then the Spitzer Space Telescope, it's in the infrared, about 3 to 4 micrometers. You basically see with Spitzer where the mass of the galaxy sits, right? So where most of the stars are. So you can weight the galaxy. It's pretty cool. So we now have a sense of how many stars the galaxy is forming that's not obscured by dust. We know how massive the galaxy is. And with ALMA, we can now look through the dust and search for those, what I mentioned earlier, the hidden star formation, right? And from the continuum.
And one of the other things you get, which is scientifically less exciting for most questions, but is being asked from one of our audience members, you're actually getting at their orientation in the sky. That's why the red is on one side and the blue is on the other.
Yes, exactly. And that's the last panel here. So you can actually see the motion of the galaxy.
And so you're able to get at how coordinated that rotation is by looking to see how much the red is focused on one side, the blue is focused on the other, versus having patchy motions all throughout the galaxy.
Exactly, yeah. So what we measure is basically what we call the velocity dispersion. So how patchy the gas is moving, right? And if it's very ordered, like a nice disk galaxy that you see edge on, then you see like this nice butterfly, right? Where you see blue on the right, on one side and red on the other side.
Now,
And this is why we see this a lot in those galaxies, which is very exciting.
do you happen to know the license plate number for this particular galaxy?
I think this is
It's all right not to know.
it's eight six something.
So someone in our chat was asking. So in looking at all of these systems, did you find that they were a mix of activity levels? Did you have quasars mixed in with more staid galaxies?
We do have one quasar, a low luminosity quasar, but how we select the sample is actually we try to select basically normal galaxies at this time. But there, so what there is this so-called main sequence. So when you basically compare the star formation rate, so how many stars the galaxies are forming versus stellar mass,
Yeah.
you see that those galaxies most of the galaxies are actually on a nice line. So they correlate. So when you have more mass, you have more star formation. If you have less mass, there's less star formation. And so this is the star forming main sequence. And that's pretty interesting. So that's basically throughout the universe, galaxies, they just sit on this relation. The relation changes in normalization, right, up and down with time, but they're basically all plus minus some scatter on this relation.
Now,
And this is what we consider the normal galaxies, and this is how ALPINE was selected.
now in our own galaxy, we are looking at basically a couple of stars forming per year, nothing too dramatic. What kinds of star formation levels were you finding in your systems?
Yeah, so this is really cool. So the lowest we have in our sample is about 10.
Uh-huh.
The
The
highest is
lowest.
about the lowest, and the highest is about 300. So on average, they're like forming maybe 100 times more stars than our Milky Way at that time.
That's
And the galaxies are much smaller, right? So if you go maybe to slide 13, you can actually see the size of those things. So they are obviously, galaxies, they grow over time because they accrete stars, they form stars. And so they are much smaller, but they form many more stars, right? So here you see the Milky Way in comparison with those images from ALMA.
now
And so they are very compact and form a lot of stars. So
to do a quick comparison. I know one of the really frustrating things about galaxies is you look at them in different colors and they appear completely different sizes. When we look at the singly ionized carbon data from ALMA, what does that basically correspond to if we are throwing a filter on a telescope to look at a nearby? Are we seeing the same distribution of galaxy that we'd likely see in visible? Are we seeing more like going further out like we would in the infrared? What part of the galaxy are we sampling with this?
So what you actually said is correct. So with carbon is actually more extended emission than what we would see in stellar light, right? So if you would look with Hubble at those galaxies in the visible light, they would be smaller. And this is cool because it tells you that the carbon is not only where stars are forming, this carbon is also diffuse in the galaxy. Yeah, think of it like a gas halo around the galaxy, right?
And so we're seeing star formation throughout the entirety of the galactic systems.
Yeah.
And we're able to see a further dispersion than what we casually see with the backyard telescope looking at nearby objects, because we're just sampling that much further out into the wings.
So yeah, so there are basically two things, right? So one, you can be very dusty out there, so you just don't see it because it's dust obscured.
Right.
Or the carbon is emitted in very diffuse, warm gas, and that's farther out in the galaxy.
Now, some of the folks in our chat are asking questions trying to tie together all of these ideas. So if you were to look at the relationship between amount of star formation and amount of dust as a function of time, how would those two variables change from when you're looking here to what we see today?
So dust is built up over time. So although we see, as you see from the pictures, right, there's a lot of dust in those galaxies.
Yeah.
It's not nearly as much as we see today, right? So dust is increasing over time. Star formation is increasing over time as well.
The rate or the number of stars in total?
So the rate, so if you go to slide 4, actually, I think I have the... So the rate of stars is increasing in the early universe.
And then it just nosedives.
And then it nosedives, right? So this is when you look at redshift 2, or about 3 billion years after the Big Bang, when the whole thing peaks. So this is the time versus the amount of star formation in our universe, like a star formation density. It drops, right? And this is where galaxies start to die, right? So they used up their gas. So in the very early universe, where this blue bar is, that's where ALPINE is looking at. So it's basically where the rate of star formation is increasing like crazy, right? And this is why it's very important to look at this epoch, because this is where galaxies are actually start to form, right? And they have a lot of gas, they have not much dust, right? And they're forming the dust over time. They decrease deplete their gas over time because stars are forming out of the gas. And at some point, about 3 billion years after the Big Bang, the gas is depleted and star formation is starting to shut down. Right, and that's when they get red and dead, how we say.
So the overall picture that we're looking at is the universe starts out as this almost smooth blah of gas.
Mm-hmm.
The gas gravitationally falls in. We're ignoring dark matter today. Gravitationally falls in, and gas gets turned into stars. Stars turn gas into many things that include dust. And so it's because we've had stars that we build up dust over time. And so we have basically the stars hiding themselves behind dust as the universe evolves.
Exactly, yeah. And you can have, what's cool is you can actually have winds and pressure from the stars that move away the dust. And so at some point you start to see the stars because the dust is blown away, right? So they start to appear, right? And this is also what we can see in our data, right? It's like a local, like a kind of a patchy dust screen that we see, because we see some light from Hubble, but then other parts of the galaxy is just obscured. And this is part of the, as you say, like dust is built up, it's blown around, it's when galaxies collide, it's just thrown into the universe. And
the universe was smaller at the time that you're looking.
Yes.
How did that affect the density of galaxies relative to one another at this time? I know large scale structure was also still forming, so you have this complicated dance between, well, the walls weren't as dense, the voids weren't as empty, but the universe was smaller. So how did things compare?
Well, you have much more interaction between the galaxies, right? And you have more gas, as you say. The gas is still falling onto the galaxy, right? The hydrogen to form the stars. So you have much more inflow of gas into the galaxy, and that triggers star formation. So that's also why we think the reason is why galaxies are forming so many stars at such early times. Right? It's basically like a firework of star formation, right? You have gas inflow that triggers star formation. You have galaxies colliding. It's kind of a mess, right?
And it's the mess that we enjoy studying sometimes. Nice, neat
Exactly.
systems don't keep us interested for nearly so long.
Exactly.
And what you're looking at, any of these systems could have grown up to be something like our Milky Way, like the Andromeda system that we're used to. But we're catching them at a moment where you just described the gas is still falling in, so they're still gaining mass. Stars are still forming. Dust is being pushed out. How long do we know did it take to go from this vibrant chaos to, well, having systems that are more placid that we're used to seeing?
That's a very good question. So I would say around redshift of 2, so about 3 billion years after the Big Bang, things start to calm down. And that's also when we see this, the galaxies dying, basically, right? Stopping their star formation. We are here at about 1 billion years, so I would say maybe 2 more billion years and things calm down, right?
Yeah.
But you said actually the stellar mass and how massive those things are. So that's actually interesting. So some of those galaxies in our sample, they have about 10 to the 10 stellar masses. So you can think of like 10 to the 10 stars, right?
Yeah.
So 10 to the 10 times one sun. And if you just let them grow, right, they would reach masses that are 10 to the 12 or more in the local universe, which is actually more massive than the Milky Way. So some of those galaxies already there are so massive, if they would just grow, they would become monsters in our time, right? They're huge. But that probably doesn't happen because the more massive a galaxy is, the more likely it is to die earlier.
Right.
Right. So because they form stars at such a high rate, which means that they're depleting their gas also much faster, right? So we think that some of the very massive galaxies that we see at these times are will become those passive, dense, red elliptical galaxies that are supermassive in the local universe.
And this is where it really starts to become a matter of nature versus nurture at about 2 billion years. In the early universe, the infalling stuff, at a certain point, the galaxies are like, okay, quasar turning on, blast, and that just kills everything.
Yeah.
And then gravity takes over. And so it's how big a cluster do you end up in? And at about 2 billion years, you start finding that systems that had the misfortune of landing in massive galaxy clusters, they're going to have a very different evolutionary path than a galaxy like our own that ends up in a tiny group. But prior to that 2 billion years, it seems very much like it's every galaxy for itself. And that's an awesome difference in evolution.
Yeah, that's true. And we actually already see at this time that there are so-called protoclusters forming. So, for example, some of our galaxies, they are physically related, right? So they are in, Milky Way Andromeda distance to each other, or even closer, which means that they are forming this kind of cluster environment at that time, and that obviously evolves over time, and they accrete more galaxies, and then you have like those
and some of these
clusters that you see today, right?
And so you're catching things in the early moments of figuring out how big a clique they're going to be in someday.
Exactly. Yes.
Now, this is cool research that I have to admit I could talk about all day long, but neither of us can do that because unfortunately both of us are blighted with having telecons we have to go to, because they don't tell you in graduate school that really 90% of being a researcher is being on telecons. What are the things that came out of this that you think it's most important for people to know? That if you could just like stand up at a AAS meeting and shout, "Know this thing," what is it that you would want people to know? Not that you would ever do that. No one would do that. It would be interesting if someone did that.
Yes, so there are a couple. So one is that we actually now can study how dusty those galaxies are. So generally, there is less dust in those galaxies than today, but there are some galaxies that are super dusty. So, right, it's the variety of galaxies that surprises us, basically. And the same for the structure of the galaxies, right? So most of them are merging. They're like colliding with each other. They are irregular as expected, but some are already rotating and have nicely ordered gas motions, which also is a surprise, basically. And then the other thing is what we actually can do now is to trace the star formation rate back to those very early times. And with ALPINE, we have learned a lot about that too, right? That there are those dusty galaxies out there, and the star formation might be on average higher than what we thought before, because before we just thought, no, there's no dust. There can't be dust, right? Because they don't have time to form dust. But actually, that might not be true, right? And these are the interesting things that I think this survey is showing now, and we are still working. There are like at least 6 papers in production that have a lot of interesting stuff in it. So, and then obviously we prepare for JWST and
Of course.
which might combined. And so yeah, it's basically ALPINE is like the base for more, right? It's not, it hasn't stopped.
It's a pathfinder that is defining the
Yes.
way for everything to come behind.
Yeah, it's defining this very important sample where we can build on with future telescopes and learn a lot more about those galaxies.
And so we have folks in the chat just working to make sure they have this story straight. And so Astrowise, I'm going to try and sum this up for you. So the gas gets used up to make stars, and the stars produce dust. And as the stars die and explode, this just creates more dust. So it goes from gas, which is like individual elements. So like you have an oxygen, you have a nitrogen. Well, you don't really see the nitrogen. You have an oxygen, you have gases. So like carbon monoxide, carbon dioxide. Dust is structurally more complex. It's not just a single molecule. It's a bunch of stuff glommed together, and it affects light differently. So we go from gas going into stars. Stars make dust. Is that? Did I say all of that correct? Okay.
Exactly. Yeah. You basically start off with nothing, no dust, no metals, and the first stars, when they explode, they throw out all the amount of dust and metals.
And so what we're really seeing is the toddler and teenager pics of most of these galaxies when they're still throwing temper tantrums and having awkward moments in their growth cycle.
Okay. Yes, that's the teenage galaxies, I would say. Yeah, they're growing a lot and producing dust.
and they're not fully formed yet. They still need to get their arms on.
Exactly, yeah, they still need to shape.
That is kind of awesome. Now you've already hinted that you have a lot of papers still in the pipeline for this. Can you give us any hints or sneak previews of what is yet to come?
So there is going to be a very interesting paper by a group in Geneva that talks about basically what you said. So enrichment of the interstellar medium, so the medium between the stars in the galaxy with metals and dust. So that's going to be very interesting. And we also have some papers about outflows, so we can measure how fast gas is flowing out of those galaxies due to the pressure from stars, right? And so they lose the gas, but they don't lose it as fast, or it doesn't fly away as fast as it can escape. It will fall back onto the galaxy. It's kind of fun.
So DPI,
and it remains.
DPI 209 is commenting that these are teenage mutant ninja galaxies.
Yeah. Some of them you can't see. That's the thing. Yeah.
And this is just really cool research because it brings together all the complicated physics that we've only really been discovering in the past 20 years. And when you say star pressure, I just want to make sure that people understand that it's not like the stars are themselves moving around, exerting pressure on things. It's the stars' light. It's the shock waves of exploding stars. All of these different things build up. Light is a pressure, and stars exert pressure through their light.
Exactly. Especially young stars in those galaxies that are super hot and super young. They just emit like a ton of light and winds and everything.
So you are one of the astronomers that has come on that actually has a Twitter account that we can use to follow what you're doing.
Yes.
What's your Twitter account?
It's at Astrofeist, Astro like Astro, and Faisst.
Yes, and your name is conveniently typed underneath you right now. So everyone, go out, give him a follow. And if folks wanted to find your research on the IPAC website, where would they look?
They look at alpine.ipac.caltech.edu.
And so folks, go take a look at all of this. It's really cool stuff. And when you have more science, I'd love to have you on again to talk about how you're changing our understanding.
That was fun, yeah. Happy to.
So this has been a fabulous interview. Do you have any parting words for our audience?
Well, so I'm also involved in outreach a lot. So if you are in Pasadena, well, now you can see it everywhere, but we have a lot of public lectures that are super interesting by CalTech folks. And so I would encourage you also to look at our outreach programs to learn more. And yeah.
Next time I'm out in the LA area, hopefully we'll be able to meet in person. But first we need to get through these plague times. But before that, we need to get through telecons. So I'm going to let you go here. Thank you once again. This has been great, Andreas.
Thank you for inviting me.
And audience, thank you all for being here. This has been The Daily Space. I'm your host for today, and I wrote our script. My name is Dr. Pamela Gay. We are joined by special guest, Dr. Andreas Faisst. And today's episode will be engineered by our own Paranor, Tim Hawkins. We are a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to the generous contributions of people like you. Your bits, your subs, your patronage at patreon.com, they let us keep the light on and keep our staff paid a fair wage, which we're so grateful that you let us do. Now, we understand if right now keeping food on your own table is a hard enough job. You eat. That's your priority. We'll figure out how to keep going no matter what. So just be here. And know that we have a vibrant Discord community where you can come hang out, talk science, find ways to volunteer, and even join us in a game of Ticket to Ride. So wherever you are in the world, we're here for you. And I see those bits. Let me see if I can bring up dog cam. Hold on. I'm going to bring up a stupidly large dog cam behind me is what I'm going to do. Hold on. Finding the correct combination. There we go. There are the doggos. Are you ready? Do you want this? Do you really, really want this? Thank you for all of your bits, humans. Thank you so much, Wayne Johnson, and to all the rest of you who have contributed today. Stella, you've got to jump out of the chair. I have the laziest dog sometimes. So thank you all so much. You help keep the science flowing. Now I'm going to go ahead and take a look and see who I can find to raid so that we can keep this science rolling from place to place to place. Econ Greg is doing solar observing. That sounds excellent. Just a moment and I will pull that up. Having a moment of not there. There's the button. All right, everyone. So go observe the sun safely. Have a fabulous morning, evening, or afternoon. Wherever in the world you may be, wash your hands, wear a mask, and if you like people, stay inside if you can. We'll see y'all later. Bye-bye.